Hello everybody, and a very warm welcome to the presentation of our work, Latency Optimized Architectures for Real-Time Inference Pipeline for Control Tasks. My name is Florian Schellroth, and I wrote the work together with Yannick Lehner and Alexander Ferl. Now, computer vision is already incorporated in our everyday life. If you own a smartphone and you can unlock it with your face like this, you're already using some sort of computer vision to detect your face and recognize if it's you or somebody else. And the same principle goes for other fields, like for example FarmBeats, a project from Microsoft. Here, a field is scanned and detected whether or not the crops are ready or malicious, if they have to be treated or something else. Moreover, computer vision is already implemented in our manufacturing. Like in this case, where a robot uses a camera to detect the cable and decides where he needs to put the gripper to perfectly grip the cable. But this problem is static. Like the robot has enough time to take a picture statically and calculates where the object is and how it is rotated. What happens if we have a dynamic case, like for example with a moving cable or with some object which is driven around the manufacturing unit? Or in other words, we want to use computer vision as the input to a controller. But a controller needs a relatively new input, which means the temporal distance between the object which is moved around the manufacturing unit and the final input to our controller should be minimized, or the latency of our computer vision should be minimized. But first, we need a fundamental understanding of the neural network. On the bottom left, you see the neural network depicted. And it consists of mainly three different types of layers. First, the input layer, where all the input is fragmented into single neurons. Then, one or many hidden layers, where nonlinear units try to approximate a desired output by training. And finally, the output layer, where the last hidden layer is capped to a maximum. In our case, we want to use convolutional neural networks, where the hidden neurons use a convolutional activation function. This provides a feature of perceiving spatial information throughout a picture, which is essential if you have XY coordinates and you always want to know which pixel is next to the other pixels. To calculate a neural network's output, inference is used, which is a layer-wise calculation of all layers in consecutive order. And since hidden neurons are not interconnected in the same layer, there's a parallelization possible in a layer-wise manner. Now, as previously stated, we want to use computer vision as the input to a controller. In our case, it's a programmable logical controller, PLC. And a PLC consists of three stages. At first, we copy all input from the sensors to our internal PLC memory. Then, the whole control program is executed. And lastly, we provide output to the actuators, like for example motors. And if this one is finished, we go back to the first one. So a PLC is executed in a cyclic manner. And there are some side notes. Off-the-shelf PLC hardware cannot process CNNs in typical industrial cyclic times, like for example 1 to 10 milliseconds. So we need to accelerate with additional hardware. This is already shown in recent works. Here, CNNs are interferenced on GPUs instead of CPUs, and the result is pushed back to the PLC. This type of real-time GPU usage next to PLCs for hardware acceleration is shown in the literature. In our work, the PLC is hosted on an HX Xavier board by NVIDIA. This is an embedded controller with a shared memory between CPU and GPU, allowing to share data between the both with minimal latency. and thus allowing hardware acceleration of the PLC with almost no latency in data copy. And with this, we can formulate a problem statement. How can the individual tasks of the inference pipeline be executed so that the pipeline becomes optimal with respect to the criteria? First, a low overall pipeline latency. Second, ease of implementation, so the hardware acceleration can be widespreadly used. And lastly, the exchangeability of components. The last criteria is especially important for the use in Industry 4.0 implementations. In the next slides, we want to briefly introduce how different architectures of the inference pipeline are possible and how the worst case latencies of them are calculated. On the bottom left, you see two of our four components. The camera on the bottom, which constantly pushes data, in this case pictures, to the image preprocessor. And above is the PLC, which runs in a cyclic manner. Between those is firstly the image preprocessing. In our case, the image preprocessing is executed right after the camera pushes its data. Above is the inference engine, which is hosted on the GPU. In the first architecture, we decide to cyclically execute the inference engine with the last given image by the image preprocessing. We start with the blackly labeled camera image. This image is directly passed to the image processing and then led to the inference engine, which recognizes an object and sends its position to the PLC. In architecture 1, since everything works asynchronous in a cyclic manner, it's possible for the PLC to exactly match with the inference engine and the image preprocessing exactly matching with the inference engine. So one image preprocessing cycle and one inference cycle is missed, as shown here. In architecture 2, we synchronize the inference engine with the image preprocessing. So every preprocessed image is directly sent to the inference engine, which then detects the object. Last but not least, there's a third architecture, which is a little bit more complex. Since our PLC shares the same memory with our convolutional neural network, it is possible to exchange data even during the PLC cycle. Thus, it is possible to pre-calculate when the inference engine should finish its job, right to pass the extracted data up to the PLC. Then we only can miss one image preprocessing cycle and one of those post-processing cycles on the PLC, which is shown as the remaining PLC cycle in the legend. For those architectures, we conducted an experiment whose results are shown in the table below. We used the previously mentioned NVIDIA Jetson HX Xavier board in the development version, which has the specs shown. To evaluate our latencies of all the components, we use different types of evaluations. Let's start with the camera. We want to use a 100 frame per second camera, which has a CSI2 input to our microcontroller. We estimated by search in the literature that the latency, including some buffer time, will be around 10 milliseconds. Next is the image preprocessing. Here we used OpenCV to scale and crop 5,000 images from 640 by 480 pixels to 416 by 416 pixels. And our worst case measurement of this scaling and cropping came to 5 milliseconds. Next is the inference. Here, a wide variety of benchmarks is commonly available in the related work. We used a benchmark by Wang et al., which benchmarked our desired CNN, the tiny YOLO V2, on our board, the NVIDIA Jetson HX Xavier, and measured an inference time of 4 milliseconds. Next is the PLC. Here you can choose the cycle time by yourself, which we've done extensively in the previous work. And we settled down with a cycle time of 10 milliseconds. Lastly is the output processing. Here we estimated that the output processing, which basically is a nonlinear controller with limited computational effort, is around 2 milliseconds. The whole experiment comes together in a comparison table, which shows all three architectures, their maximum latencies, the maximum latencies from our experiment, our criterion of the ease of implementation, and the criterion of exchangeability of components. The difference in maximum latency between the architectures is as follows. Between architecture 1 and 2, there's a difference of 1 tau inf, which basically comes down to the asynchronous manner of architecture 1 between the image preprocessing and the inference. Between architecture 2 and 3, the difference is between tau PLC and tau output processing, which comes to the enhanced method of synchronously pushing up the output data from our CNN to the PLC right in time on shared memory. In values, the maximum latencies from our experiment are 33 milliseconds for architecture 1, 29 milliseconds for architecture 2, and 21 milliseconds for architecture 3. So architecture 1 and 2 are pretty close together, and architecture 3 is quite faster than the other two. In terms of ease of implementation, architecture 1 is by far the easiest one. Since all the components work asynchronously, there's no synchronization effort whatsoever. In architecture 2, we need to synchronize the image preprocessing and the inference tasks, which lowers the ease of implementation. The third architecture needs both a synchronization of inference and image preprocessing and inference and PLC. So it's by far the most complicated implementation. Our last criterion is the exchangeability of components, which is especially important in Industry 4.0 environments, where service-oriented architecture is implemented. Here, architecture 1 is by far the best exchangeability, because every component is autark in its own, so there is no synchronization effort between any components or any messages except for the data which is pushed. The second architecture needs some links between the image preprocessing and the inference components, which is why it's a little bit less exchangeable compared to architecture 1. Since architecture 3 needs a understanding of the timings of the PLC before the inference can be started, this architecture is not exchangeable in service-oriented architecture. As a conclusion, in order to enable the use of CNNs for real-time critical control tasks, we not only need the inference to be optimized to satisfy the real-time constraints, but as shown in the previous slides, we must also lower the latency of the whole inference pipeline, so that the latency between the sensor, in our case a camera, and the PLC output is minimal. Thus, in this work, we compared different architectures for the inference pipeline against certain criteria. First, of course, the overall latency of the inference pipeline. Second, the ease of implementation of all three architectures. And lastly, the exchangeability of components to be implemented in an Industry 4.0 environment. It came out that architecture 2 is the most balanced architecture in terms of overall latency. The ease of implementation was quite good, and it was still exchangeable even though certain synchronization efforts between two components have to be established. In future works, we want to experimentally verify the architectures on a real-world control task and realize an exchangeable pipeline service. This was our presentation. I hope you liked it. If you have any questions, feel free to ask. Thank you.